Hello, I am Václav Novotný and welcome to the tutorials of energy sources and conversions. In this first tutorial, after a general introduction, we will talk about heat and fuel which can provide this heat and its properties like heating values. So at first, let's ask ourselves a question. What is actually energy? The energy is a scalar physical property and it's typically characterized as potential of matter, fluid, or for example field to perform some work. Now, what types of energy do you know? There can be different forms, like for example mechanical energy, as you can see here, and under mechanical energy we can have kinetic, potential, and even then the potential energy can be further classified into gravitational energy, elastic energy, pressure potential energy. Then for other types of energy we can have, of course, electrical energy, so-called electricity, magnetic energy, radiation energy, and we can go on, for example, to internal energy, where internal energy further can be classified as energy as heat, nuclear energy of the bonds between within the atoms, or chemical energy, which are chemical bonds between atoms or molecules. Now, what is actually the source of energy? Is there anything like the source of energy? Because when we have, for example, sun provides radiation energy for us. But is it the original source where the energy appears from nothing? There is nothing as pure source of energy, because source of certain type of energy is just a conversion machine from different energy forms. For example, the sun that I mentioned is converting a nuclear energy into radiation, or a power plant is converting energy of fuel into electrical energy. Your domestic boiler is also source of heat, source of energy, but it just converts a fuel. Now let's go to our first problem. The task is to determine required mass or extent of various fuels or other energy sources for annual heating demand of a family house. This family house have, let's say that they have annual consumption of heat 20 megawatt hours. So first thing to note, how to convert energy units. You definitely know the megawatt hours, which we have here, and also other unit of energy is joule, or its multiplications as megajoule, gigajoule. So 1 megawatt hour is 3600 megawatt seconds, because 1 hour has 3600 seconds, and watt second, you might know that is a joule. So megawatt second is megajoule, that means 1 megawatt hour is 3.6 gigajoules. The 20 megawatt hours, that is our heating demand, is 72 gigajoules. Now let's have a look at the fuels and sources of energy we will look at. Those are different types of coal. You can see the black coal and brown coal, they have relatively high heating value. Then the brown coal, which is used for power plants, for example, you can see that the heating value is much lower. It's basically just a dirt that almost accidentally a little bit burns. Then we have a natural gas, we have dry wood, coke, light heating oil, and then two, let's say, a little bit specific sources of energy or kind of fuels, which is uranium-235, the fuel for nuclear reactors, and then the sun, which in Czechia the annual solar irradiation is about 1050 kilowatt hours per square meter. How do we get the amount of fuel that we need? The energy, Q, that we require for the heating is mass of the fuel multiplied by the fuel heating value. For example, what we use typically for the fuel is the lower heating value marked as Qn. Then from this we can easily write that overall mass of the fuel is our annual requirement of heat divided by the heating value Qn. Similarly, for example, for natural gas we have the volumetric values. We have the heating value per cubic meter. So the volume of the fuel for 1 year is required heat divided by Qn volumetric, or for the required area of solar thermal collectors we have the annual solar irradiation per square meter. So the area of solar collectors is just annual heating demand divided by the annual solar irradiation. This all assumes that there is 100% efficiency of conversion, or especially for the solar irradiation, that the generated heat can be stored so that we don't get into problems of having not enough sun but requiring the heat. Now let's go to the uranium as a fuel. So we had for uranium the 204 mega electron volts per single fission. And how to get the mass of the uranium that we require from this? We will use the conversion that single electron volt is 1.6022 times 10 to the minus 19 joules. Then we will require the Avogadro number marked an A, which is 6.022 times 10 to the 23 particles or atoms or components per single mole. Okay, how to go on from this? So the energy per single fission is, we have it here, 204 mega electron volts multiplied by the 1.6022 times 10 to the minus 19 joules per electron volt. Now here we have mega electron volts, here we have joules. We will want the energy of the fission pair in joules, so 1 mega electron volts is 1 million electron volts, so we need to multiply this times 10 to the 6. And if we have it right, so we should get value 3.268 times 10 to the minus 19 joules per single fission. Okay, now how many fissions we need to perform in single year? Our annual heating demand Q was 72 gigajoules, which is 72 times 10 to the 9 joules. And here we have energy per single fission. So let's call this N, number of fissions in single year. Which is nothing than just the heat divided by energy per one fission. Once we put it together, we will get the result that we require 2.203 times 10 to the power of 21 fissions in 1 year. Okay, so we have number of fissions, but still we need to get the mass of the fuel. For that, first let's get the mass of single uranium atom. Now let's get a mass of single uranium atom, where the molar mass of uranium-235 is surprisingly 235 kilogram per kilomole. Or also 235 gram per mole. So the mass of single atom of the uranium-235 is the molar mass divided by, and now here the Avogadro number. So the mass of the single atom is 3.902 times 10 to the minus 22 kilograms, grams, because we use the Avogadro number in moles and 335 gram per mole. Then getting it to kilograms, so it's 3.902 times 10 to the minus 25. And now we are just one step from amount of our uranium that we need in single year. So, and U-235 in single year is mass of one atom multiplied by number of fissions in a year. So, getting this together, we will get value 0.0008597 kilograms. But the question was, how much of the fuel as uranium-235 in a year do we require? And when we have the fuel containing U-235, typically it's not 100% pure uranium-235, but the concentration of this isotope of uranium in fuel for example, light water reactors is about 3.6%. So, concentration U-235, and fuel is 3.6%. So the mass of U-235 fuel, where the rest of the fuel is mostly just uranium-238, is now the mass flow, the mass of the uranium, of the pure uranium-235 required, divided by this concentration. And we get that for this type of fuel we would use 0.238817 kilograms in a whole year. So 200 grams, like let's say package of cheese, of uranium fuel would be enough to provide the heat for your family house for the whole year. Now let's have a look how is it with the other types of fuels regarding the results. So we got successfully to the value of the demand of the uranium fuel, which is about 24 grams per year, And now we can go, as I have shown you before, the method how to get the requirement for the other fuels. So the required amount of fuel is the yearly production, here 72 gigajoules. We can convert the gigajoules to megajoules so that we have the same units as our heating values, here mostly lower heating values, and divide it by this lower heating value. So we have about 2,400 or almost 2.5 tons of 2.5 tons of black coal. We can do the same for the rest of the values. So if it's brown coal, it's already more than 4 tons. If it would be the brown coal used in power plants, so it goes up to 6 tons. Natural gas is more than 2000 normal cubic meters. The cubic meters that are measured in natural gas, so those are so-called normal cubic meters, meaning natural gas at specified temperature and pressure, typically 0 degrees C and 101 kilopascals. Now for the wood, it's also roughly 5 tons, as a little bit more than for the brown coal. The coke is, as you can see, comparable with the black coal. Light fuel oil, a little bit less than 2000 kilos. And now for the solar power, so in theory the ideal amount of for the solar power, the ideal requirement of the area, since we have the provided heat in kilowatt hours per square meter, so we need to use the produced kilowatt hours, megawatt hours multiplied by 1000, and now divided by the yearly irradiation, and we have roughly 19 square meters. But this is in case of ideal conversion, but as we know, in thermodynamics and in nature nothing is perfect. Just your girlfriends or boyfriends would probably be unhappy to hear that. And the real requirement of the fuel or of some resource needs to be corrected by the efficiency. So here we have typical values of operating efficiency of some smaller size boilers, and now we get the ideal requirement and just divide it by the efficiency. Now, why is it divided by the efficiency? The efficiency is a ratio of, let's say, product over resource, or it can be also seen as the some real, for example, real work compared to ideal work, or for example, output to input. Now, in our case, the efficiency is the ratio of heat which we get out of the boiler. So, out to heat in the fuel at the input. So now, and the amount of heat in the fuel input is the parameter that we want to get. So you can see that for getting that, you need to divide the boiler output by the efficiency. So we go back to our problem, and yeah, we get the actual requirement with this simple formula. Just for the uranium, we don't consider any efficiency because this is just like, you anyway would not use uranium fuel for heating up your home, but it is mostly to see the extreme difference between amount of other fuel and resources compared to the very small amount of nuclear fuel. So as I said, the efficiencies are like efficiencies of the boilers for continuous operations, including starts up and shutdowns, which you can consider. And for the sun, this is still a little bit probably optimistic efficiency of solar thermal collectors. In the second part of today's tutorial, we will have a look at in more detail into the fuel, its composition and analysis. The composition of fuel. The fuel contains multiple components. It's basically never some like pure single piece of matter, and we distinguish between them. There is the combustible part, which we denote as H, which contains the active constituents, the components that form oxides and that release energy when burning. Then the passive constituents, which are also released into the gaseous form, but they don't produce oxides, they don't release energy like nitrogen and oxygen. Then there is ballast, which is the ash and water. Here we have a few simple formulas, where of course all the components together, combustible, ash and water, are one. And now we have other one, which will be more described in next slide. So we distinguish between different state of the fuel. So-called original or received state R, which is the fuel as you get it. Then so-called analytical form, but mostly the dry form, D, after the water is evaporated. And then we have the combustible constituents only, which means, as we could see, the combustible is H, so it's without the ash and without the water. So also this is called dry ash free and denoted as DAF. So here we have some simple formulas how to how to calculate one form from the another. So for example, ash in the form of received is ash in the dry form multiplied by 1 minus the water in the received state. Then some components, for example carbon, but also same for other combustible, in the received state is the dry ash free multiplied by 1 minus and what we subtract from that, which is the water in received state and ash in received state. And here, for example, in the dry state, it's dry state and dry ash free. So we have for example, here carbon in dry, carbon in dry ash free multiplied by 1 minus ash in the dry form. Now let's just have a look at some typical fuels and its water and ash content and lower heating value. So we can see that the brown coal typically can have rather high water content compared to black coal or anthracite. Also, the brown coal typically has a very large amount of ash. That's what I was talking about, that that the brown coal for power plants is basically just a dirt, and the combustible content which burns is very small. Then for the black coal and eventually anthracite, the ash content is getting lower. For wood, it has very small ash content, but its water content can range quite significantly from just around 10% of the completely dry wood after having it stored, for example, in barn or in some dryer for a longer period of time, to 60% in the state when you just chop the tree and want to burn it. Here we have example of the combustible content composition, where we have carbon, hydrogen, sulfur, oxygen and nitrogen. And we can see, for example, that the carbon content is really very high for the anthracite, while, for example, for the crude oil, as it's the hydrocarbons, so there is a relatively large content of the hydrogen. Also, for the sulfur content, you can see that some coals can have relatively high sulfur content. Very low sulfur content is in wood, and relatively large sulfur content can be also found in crude oil. Now, before you heard expressions like lower heating value or higher heating value, and now we will have it explained what it is and what is the difference. So the definition goes that the lower heating value is the heat released from combustion of 1 kilogram of fuel and cooling down the flue gas to 20 degrees C. And the important part here is that cooling down while the water for the lower heating value stays in the form of water vapor. That means it does not condense. The higher heating value definition is similar, but just it says that the water content condenses. So it means the higher heating value is, well, of course, as the name says, higher. Lower heating value is lower by the condensing heat of the water content. We can see that also in the equation here below, where we have the lower heating value, Qn, is the higher heating value minus the heat of water evaporation at 20 degrees C. And now let's go to our second problem in this exercise, in this tutorial, where we have given fuel composition, and our task is to determine the received state and estimate the lower and higher estimate the lower heating value. And the composition of the fuel is here in the table. So the calculation of the received state is kind of straightforward, as you can see from the equation here. The received state is the 1 minus water content, ash content, multiplied by the dry ash free. So we can quickly make the formula here. 1 minus water content minus ash content multiplied by concentration in the dry ash free state, and we get the resulting values. The second task in our problem was to get the lower heating values of the fuel for which we The second part of our The second task in our problem was to get the lower heating value of our fuel for which we know the composition. We can do that by using experimental correlation for the lower heating value, where in this tutorial I will show 3 of them. As you can see, A from one guy Dulong, B Czech author Vondracek, and C from another Czech textbook. And you can see that the experimental correlations are using certain values multiplied by the composition of each content of the contents of the combustible, or eventually the contents of the water. You cannot see the contents of the ash because the ash is just ballast and it does not affect the heating value. So now once you put the values in, so you should get these three values: 23.7 megajoules per kilo for the first one, 23.6 for the second, and 23.5 for the third one. You can see that there is some discrepancy, but in general there is relatively good agreement because it's the composition which was given for coal, for which these correlations were developed. If you would try to use, for example, the composition of some oil or let's say wood, so the accuracy could be much lower. So this was the end of our task for today, end of our calculations, and see you at the next tutorial.